Hey everybody, tonight we have a simplify, or sometimes called a Denest problem, where we're trying to remove at least one of the radicals. I'm just calling it evaluate because I want to write this in an exact form, no decimals of course. So let's see how the approach that we might adopt here. Since you have a minus sign here, maybe we have the good fortune of expressing it as the square of the difference of two variables here, okay? Now, I wrote absolute value here because this is the definition of absolute value. 64 is a bigger number than the square root of 3772, so this would just be x minus y in this case, all right? But it turns out it's useful to just look at the prime factorization of 3772, okay? Now, 3772 is an even number. It turns out it's divisible by 4. So we end up with this number 943 that we need to factor. Now, 3 definitely is not a divisor of 943. The very well-known sum of the digits result, 3 does not divide the sum of the digits 9 plus 4 plus 3. All right. So we can negate this divide relation with this little slash. Okay. Now, also it's clear that 5 doesn't divide, but let's take a look at 7. There's a divisibility test for 7 that's kind of fun. What you do to make this thing fly is you look at the 943, you take the first 2 digits and subtract the double the last digit. All right, and so what you end up here is what is that? 688. And you note quickly that 88 is not divisible by 7. If we got a number here that was divisible by 7, okay, and 7 does not divide it, right? Okay, so we'll write this. 7 does not divide 88, all right? So that's your divisibility test for 7. And you probably could have just checked it, directly on 943, but this knocks it down to a 2-digit calculation, all right? And it's clear that 11 is not a prime divisor because any power of 11 ends in 1, right? And also in a similar fashion, folks, I won't go through all of them. 13 is not a divisor, prime divisor. 17 is not a prime divisor. 19 is not a prime divisor. And again, that's just work, folks. I don't know any divisibility tests for 13, 17, and 19, but 3, 5, 7, 11, 13, 17, and 19 are not prime divisors. It turns out the very first one is 23. Okay, so in other words, we can write this as 4 times 23. And once you discover that 23 is one of the divisors, it's real easy to find 41 as the other. Okay? So we get this prime decomposition. You can call this 2 squared, and it's a bona fide prime decomposition. And you can check that for reasonableness, this would, 1 times 3 is 3, and then 4 times 3 is the 2 that you see right here, right, folks? Again, 1 times 3 is 3, and then 4 times 3 would leave 2 as the last digit, right? So this looks believable. And so what that does, that leads for a very natural choice here of selecting x equals to the square root of 41. We want x to be the bigger one, right? Okay. And then y, actually it wouldn't make any difference, I guess. Well, the way the problem's set up, yeah, I guess it would. But so we'll take y to be equal to the square root of 23. All right. And you can see it just works very nicely from this point. Okay, so right here, you would get this part right here would be, let me come over here. I kind of painted myself into a corner a little bit. But we would have, this is x squared would be 41. Okay. Plus 2 times square root of 41 times square root of 23. And folks, you can see when this comes together, the 2 will come inside of here and become a 4, right? So, and then also the y squared will be, I'm not doing very good here, but this would be 21, right? Or 23. So you see how you get the 41 and the 23 is the 64. And let's see, that was do we got everything on the screen here? Yes, we do. Okay. So you see, from the work we've done up here, what you end up with is the square root of, again, with these selections for x and y, 41 and 23 gives you the 64, right? So I'll just write it down. All right. And then if you write this down right here and bring the 4 inside, you will get 3772. We've already seen that arithmetic work out for us, right? So that didn't. Okay, so we can write this as, maybe I should write it like this to be a little clearer. Just from the work we've done above, this would be equal to the square roots of the square root of 41 minus the square root of 23. And I think I'm barely keeping it on the screen for you guys. Okay. I think I've pieced it together enough for you guys to believe this, right? With these selections right here, yeah, x is equal to the square root of 41 and y is equal to the square root of 23. And the rest of the algebra works out nicely. And so the final answer for this one, and right here, clearly this would be the absolute value technically of square root of 41. I'll just write it down for the sake of completeness. But it's clear that square root of 41 minus the square root of 23 is a positive number. And so this is just equal to square root of 41 minus square root of 23, which is an exact answer, and it's somewhat simplified. It's denested in the sense that that bigger overarching radical was removed. Okay? Alrighty, folks. And again, I don't know, the problem was actually in some sense harder than computationally right here. All I did was kind of wave my hands about the 3, the 5, the 7, and 11. Well, I gave a little bit of justification on that, but 13 doesn't work. You just had to try. You're searching for some prime factorization, and eventually you would discover that 23 and 41, the 23 and the 41 are prime divisors also. So again, there's some tedium going on here, a lot of scratching around. But we did arrive at a solution, and this is the solution. So let's write it up here. Okay. Good night.